Hey, stats class. We're going over hypothesis testing about proportions, but I want to just call back something that we saw earlier in the semester, which was normal approximations to the binomial. So the binomial distribution dealt with P and Q and the probability of success, probability of failure, that kind of thing. But when we used the normal to approximate the binomial, it was because n times P and n times Q were both greater than or equal to 5. Well, that's being called back here. All right. When can I use the normal distribution for hypothesis testing? And hypothesis testing is going to deal with the distribution of sample proportions, and sample proportions, because there's that, the percent of the population or percent of the sample that have equality, percent of the sample don't have equality. There's the binomial distribution that's taking place there. And so we're using the z distribution or the normal distribution to approximate a binomial distribution. So we're right back to n times p and the n times q both being greater than or equal to 5 to know that we can do it. So that's really important that you understand that criteria comes straight from what we saw earlier in the semester. Now let's look at an example of that. So we got to be careful here because it's n times p. So we have p and we have p hat. So p for the hypothesis testing is controlling the distribution of the sample proportions. This is controlling the distributions of these. So this is the p that we're talking about when we do n times p. Okay, so n is 25, and p is 0.11. And there's the calculation I get, 2.75. That's not bigger than 5. Okay, so I wouldn't be able to use it here. Just notice that it's technically n times p and n times q. Q is 1 minus p. So 1 minus 0.11 would be 0.89. But you really only need to compute the smaller of the two, because that's the one that would be below 5, right? It's n in both cases, and then p and q. Well, if q is bigger than p, I don't need to worry about that one. It's the one that has the smaller one is the one that's going to be questionable. If this is too small and the other one's fine, well, it's still too small. So go to the smaller of the two and test that one. If it's okay, like if this had been 250, I don't need to test the other one because this would be the smaller of the two, and it's okay. So the other one's going to be okay. It's just if it's not okay, it's definitely going to come from this one, the one that is the smaller of p and q. All right, but note this is n times p. N times p is less than 5, so we can't use the normal or approximate the binomial in that case. And then on this question, because I don't have a normal distribution here, just the choices are always the test can't be performed all the way down. Right, here is another example, very similar. It's just giving me a different claim. So claim p is not equal to 0.27. So that's the p I'm going to use in the calculation. N is 100 here, so 100 times 0.27, that's 27. I don't need to do the other test. That's the n times p. N times q would be 100 times 0.73, and 0.73 is bigger than 0.27. So since this is big enough, the other one's going to be big enough. So that means, yes, both of these are greater than or equal to 5. So I can do the normal approximation to the binomial. Okay, this is the claim. The claim is not equal to, so that's the alternate hypothesis. That makes the null hypothesis be equal to. So that's going to be choice B, not equal to, equal to. So always opposites, and from the null to the alternate has to have the alternate has to have strictly inequality. So not equal to is the inequality here, and that means equality in the null. If we want to get critical values, we need to pick the right test. Since this is about proportions, a hypothesis test about proportions, that's the z distribution or the normal dist. Right? Just open a parentheses, close it, because it's the standard normal to get critical values. We want to select cumulative probability. Critical values are in the the Z distribution critical values are bounds, they're not area. And these are outer, these are the tails. So I'm going to just pull this over so you can see that I've got the tails selected. All right, alpha is 0.05, that's what I'm going to put in the value for the tails, 0.05. And then these are the two critical values. So plus and minus 1.96. Okay, so I'm going to select that. Make sure you type them individually with a comma. Make sure you get your decimal in the right place too, with a comma in there. So there are my two critical values. All right, the next part is the test statistic. So again, the test statistic is a z-score. It even like writes out z equals here. A z-score is a measurement minus its mean divided by the standard deviation. So I'm going to have to divide. A measurement here, when we're talking about hypothesis tests, about proportions, a measurement is a sample proportion. So that's the p hat here. So that's 0.19 minus the mean. This means the mean of the sample proportions. The mean of the sample proportion is the population proportion, which is claimed to be, even though it says not equal to, in the null hypothesis, it is equal to 0.27. So for the purposes of the hypothesis test, we assume that that's true, even if we don't believe it to be true. So it's still the value of p as far as the hypothesis test goes. So p hat minus p, right, minus the claimed p, the null hypothesis p, and then divided by the standard deviation. Okay, very important that you understand this. Standard deviation for sample, the distribution of sample proportions, is the square root SQRT, and then underneath that square root symbol we have a fraction. All right, and then it's going to be p times q divided by the sample size. So p is 0.27, 0.27 times q, so times 1 minus p. So you can do two things. You can do 1 minus p, 1 minus 0.27, or if you can do that calculation in your head, the way you do it is, you know, what do I need to add to 2 to get to 9? That would be 7. And then what do I need to add to 7 to get to 10? That would be 3. So 0.73. So I would just write it as 0.73 personally, but you can also just do 1 minus the value of p. And then divided by your sample size. Okay, this is not degrees of freedom. This is sample size. So I'm going to do 100. Right, so there is my test statistic, negative 1.80. All right, let me move my head out of the way so I can check my answer. All right, so again, make sure that you understand that is our calculation for the test statistic. It's just a z-score. It looks kind of scary, but that's no different than, you know, when we saw stuff earlier this semester, like what's the z-score for 3 if the mean was 6 and the standard deviation was 2. You know, that's what we did. That was the measurement, that was the mean, and then that was the standard deviation. Now the measurement is a sample proportion, the mean is the population proportion, and then this ugly thing down here is the standard deviation. It's a z-score. It's just a z-score for sample proportion. All right, so there's our test statistic. I like to just draw this like we did before. So there is our rejection regions from what I did before when I got my critical numbers. This is my, I'm going to just copy it. That is my test statistic. So if I paste it, make 0 the y coordinate, I can see if that falls in my rejection region or not. Then you can just compare it, like negative 1.8 is not smaller than negative 1.96. But if you just copy it, paste it as a point, or write it as a point, you can see that it doesn't fall in your rejection region. And so therefore, I fail to reject. Okay, so it's going to be A or D. Why do we fail to reject? Because the data doesn't provide sufficient evidence. All right, so the wording in typical is we fail to reject the null hypothesis. But in this case, the claim is the alternate hypothesis. So if we reject the null, then we have evidence that supports the alternate claim. So in this case, it's failed to reject because the data does not, we don't have sufficient evidence to support the alternate hypothesis. So that's the reason why D is the answer. All right, now let's just go down through here. We're not giving us N, they're not giving us P, they're not telling us what's what. We have to figure it out ourselves. So right there it says the word claim. So this is going to be either the null or alternate hypothesis, and it's based on the wording. If it's got some greater than, less than wording in it, then it's the alternate hypothesis. But if you read it carefully, you'll see that it's a claim of equality. The Research Center claims that 26% would. So that's an equality claim. So this is the null hypothesis, that P equals 0.26. All right, in a random sample, this happens. Is that enough evidence to reject? Well, rejecting it would be like the not equal to. So the claim is equality, that's the null. The alternate would be not equal to. All right, so 26%, that's the claim. All right, would do it if they could. All right, so how do we set this up? We've got equality in the null, not equal to in the alternate. That's going to be choice E, and we just change this to a decimal form because it's P. So we're going to write it as 0.26, and we're going to write this. Whatever we put in the first place, we put in the second. It's, you know, it's like copy paste. It's the same thing. All right, alpha is equal to 0.01 here, so I'm going to change this to instead of 0.05 from the last one, I'm going to change it to 0.01. That pushes us further out in the tail, and then I'm going to update for the new information that we're given. So this is p hat. This is from the sample 30%. So that's p hat 0.3. All right, and then the claim is the 0.26. So I'm going to change that. All right, this is p hat P. This is 0.26. All right, that would make this 0.74. Remember, that's just 1 minus 0.26. You could also write in a parentheses if you do opt for that. And then divided by the sample size. Well, this is a sample of 700 instead of 100, so I need to update that as well. So there is now my value. I'm going to update that on the number line. All right, and now you can see if I pull this over, because of that tiny little value, that 0.01, we're not in the tail. All right, we're not in the rejection region. All right, there's my 2.41 for the test statistic. The p-value we can get from the normal DIST that we did up here. We got to go to area, because the p-value is area. And then this is not equal to, so this is outer, and we're going to make the lower number the opposite of this number. The upper number will be that number. So we'll put a, I'll make this here, right, and I'm going to make that be the opposite. So I've got a negative right there. Right. So again, this is that test statistic in the area into the tail to the right, but also doubled because it's a two-tailed test, not equal to. So it's also that same area in the left tail, and that's the p-value. Okay, so there's my p-value, and I can see that that p-value 0.016 is above alpha. So when the p-value is above alpha, we fail to reject the null. If you fail to reject, it's because there's not enough evidence to reject the claim. The claim is equality. The claim is the null this time. There's not evidence to reject their claim. That's probably the most missed thing right now in these type of questions, is that last part. Okay, because the other part is always the same. If you fail to reject, it's because there's not enough evidence. But it's the way the question is worded. If the claim is the null, there's not enough evidence to reject the null. If the claim is the alternate, there's not enough evidence to support the alternate. So it's all about where does the claim fall. Does the claim fall here, or does the claim fall here? Okay, it fell here this time, so there's not enough evidence to reject it.